So we are going to start a small new unit here that tries to quantify the process of learning, or describe what it means to quantify the process of learning. So far, we've looked at a hypothesis class. So far, we've looked at two hypothesis classes, linear classifiers and decision trees. We looked at a learning algorithm for decision trees. At no point did we actually ask the question, what does it mean for learning to be good? What does success mean for a learning algorithm? All we saw was an algorithm that could construct trees. How do you know that's a good algorithm? Do we have a theorem? So one of the sort of central theoretical questions in machine learning is, can we rigorously quantify the performance of our learning algorithm? And there are many different aspects to this. But one of the more popular approaches is to ask, given a certain concept, that is, or knowing that a certain concept exists, which is hidden from us, and given a certain hypothesis class that we care to use, suppose you give me a learning algorithm that you claim is good. I could ask, how many examples does this learning algorithm need for that concept so that you get a good approximation of the concept? Or maybe you get a perfect replica of that concept, or good enough approximation. So this is a number, right? This is just a number. How many examples do you need to learn a certain concept? And different learning algorithms might actually differ, and ones that are actually more efficient in this sense might be preferable, because they use fewer examples to discover the true concept. Remember, learning is search over functions, which means using the training data, the goal is to discover a good enough approximation for the true concept. And if I give you two learning algorithms, one of which uses a ton of data, requires a ton of data to find the true concept, and the other one somehow cleverly searches the hypothesis space and finds an equivalently good approximation with a much smaller number of examples. Clearly, the one that uses smaller number of examples is preferable. But it turns out this statement is not complete by itself, because the number of examples that are needed depends on how the learner and the concept or the teacher interact with each other. Different protocols for interaction might actually change how many examples a learner might need. Let me illustrate this with an example. Suppose there is a hidden monotone conjunction that the learner has to discover. A monotone conjunction is nothing but an and without any negations. So suppose we have a task where we have 100 features, all of them are Boolean, 100 Boolean variables. And it just so happens that maybe I know that only x2, x3, x4, x5, and x100 are relevant, and the true function is just the and of those things. Let's say you are the learner, and you know that the true function is some monotone conjunction. You don't know that it's exactly this one. So your job is to search over the set of all monotone conjunctions and find this one here. Is the game clear? Now, the question is, how many examples would an infinitely smart learner need to discover this function? Yes.
You need only one example where all these are on the other remaining zero.
So one suggestion is that you need one example, which is if you have x1 is 0, x2 is 1, x3 is 1, 4, 5, everything else is 0, and then this is a 1. And you give it to that function, and it says the label is 1. You claim that with that one example, you can learn that function. You can uniquely find that function. Is that true? Maybe not. Turns out not, because if I'll give you another conjunction that also assigns the label true, which is f prime, which is a different function. Maybe your learner discovers f prime is x3 and x100. Consider this function. X3 and x100 assigns a label 1 to this example. The true function also assigns a label 1 to that example. So you can't find, you have no, you're talking about an, the learner that explores every possible thing. There is no way the learner can pick one over the other, knowing this one example, right? It turns out that the answer to this question depends on how the learner and the teacher interact with each other. There are different learning protocols. One of them, I'm calling it protocol 1, is active learning. In this case, the learner proposes instances to the teacher and says, hey, what's the label for this example? Or what's the label for that example? And the learner can carefully select instances so that it minimizes the number of interactions. That's one protocol. Another protocol is something called teaching. Teaching involves the teacher who knows the function, who crafts an example, who crafts a collection of examples and gives them to the learner and says, here's a set of examples. With these examples and not even one more, you should be able to uniquely identify the function if you spend enough time on it. That's another way to think of it as a curriculum. A third protocol is actually closer to what happens in real life. Some source called nature decides which examples get labels. So it randomly picks examples and gives them to the teacher, and the teacher assigns labels to them, and that set goes to the learner. And this is what we've been calling supervised learning. So we have three protocols: active learning, teaching, and supervised learning. Before we look at the details of how many examples are necessary in each of these protocols to learn a monotone conjunction, are there any questions about just the mechanics of these protocols? Do you recognize that these are all different from each other? Because, and just quick show of hands or voices, which one do you think is the most efficient? Some people say first. There's one person in Zoom who says 2. Anyone else says 2? Some people say 2. Anyone says 3? Nobody likes randomness. Oh, one person says 3. Okay. Okay, so we have some bets on all of them. Let's see what happens. So let's compare each of these and just count how many examples are needed. Remember, in any of these cases, the learner does not know that the true function is this thing here. The learner only knows that the true function is something like that. It's a monotone conjunction. It belongs to the set of monotone conjunctions. The learner does not know which one it is. So let's consider protocol 1, where the learner proposes examples and the teacher labels them. And if the learner carefully selects the examples, they don't need to ask any redundant questions. So here's an example. Here is an interaction between the learner and the teacher that cannot you can't do better than. Since the learner knows that they are after a monotone conjunction, they can ask the first example, the first question they'll ask could be essentially, is x1 in the true function? But they can't ask that question because they have to give examples and the teacher has to label them. So instead of asking is x1 part of the true function, they'll ask what is the label. Well, let's pick x100. What's the label for this instance here where every feature is 1 except x100? X100 is 0, everything else is 1. And the teacher says, because the teacher knows the true function, the teacher applies this function to that example and says, yeah, x100 being 0 makes the label false. The label is false. But the only false in the example is x100, which means that x100 has to be in the true conjunction in the target function. Because if x100 were not in the conjunction, then this label would be 1. Right? Okay. What happens next? What does the learner ask next? There's an explanation for why this is the case, why x100 has to, this question is really probing about x100. Quickly summarizing that, if the label were false, which is what's happened here, right? The label is false. Then setting that particular feature to 0 makes, and everything else to 1, has made the label false. So that means x100 has to be in the conjunction because this is a monotone conjunction. Every one of these things has to be present. Every one of the required things has to be present. If the label were true, if f of x were 1, that means setting x100 to a 0 did not make the label 0. Even though x100 was not present in the input, the label did not become false. That means x100 is irrelevant. That means x100 is not present in the actual thing. This is like one of those puzzles, right? Like logic puzzles that people talk about. Question.
Would it also mean that it is x2 and x3, x4, x5 and not x100?
We are not allowed negations. This is a monotone. We know that the true target. So the question was, maybe the true function is x2 and x3 and x4 and x5 and not x100. But in the game we are playing, we all have agreed that the true function is a monotone conjunction. Monotone means no negations. Okay, let's now play the game to its conclusion. The next question can be set everything to 1 except for x99. That's really asking, is x99 in the true function? And turns out by setting everything to 1 except x99, the function value still remains 1. That means removing the feature x99 did not affect the truth of the function. That means x99 is irrelevant. I can do that for x98, 97, you keep doing that. Eventually you come to x2. Setting x2 to 0 actually makes the function false. That means x2 is in the function. Then you do x1. Setting x1 to 0 does not make the function false. That means x1 is not an f. And basically we have a series of questions that the learner has asked. And at the end of that series, for every single feature, the learner knows whether that feature is in the true function or not. That means the learner is able to get discover the true function exactly with 100 queries. Why 100? Because there are 100 features. And for each feature, the learner has to know whether that feature is present or not, which means you can't do better than this. You can't ask fewer than 100 queries. So in this case, in the active learning protocol, the number of interactions that are needed, number of labeled examples that are needed, cannot be less than 100. And we are talking about a supremely intelligent learner, which means it does not need more than 100. Any questions? I'll give you an exercise that's a tiny, a sort of a small extension of this game, which connects to the question that came up earlier. What happens if your function was, if you did not know that the function was monotone? It turns out that there's a small extension of this that still works. It's not terribly different. It's a generalization of this idea. I'll leave it as an exercise for you to solve that puzzle. Because I want to go to the next protocol, which is teaching. In teaching, it's the teacher who initiates the process. The teacher constructs a set of labeled examples and says, here's a set of labeled examples, and if you have this and nothing else, you should be able to discover the true function. And because the learner is infinitely smart, the learner can decode it. Okay. Any thoughts on what would be the smallest set of functions, examples that the teacher would need to provide for this particular function? Put yourself in the role of the person who knows that function and is trying to convey it using only labeled examples. Yes.
Can't think of the exact number, but I have an idea of what you would do. You would basically give an exact example of what this would represent. So for example, you would provide an example of x2, x3, x4, x5, and x100 being 1,
Mhm.
everything else being 0. And then the learner is basically going to go through all the different permutations of those values being 1 and basically get all the possible functions.
But that's just one example.
How many,
This was the
How
same
much does
example
the
that came up.
how much does the learner do with a single example? How much computation does the learner?
Infinite.
Well, if there's
Assume infinite. I claim this one example is not sufficient because it does not tell the learner the difference between this function f and another function g, which is x2. Because x2, g, the function g, or let's make it more complicated, x2 and x100. x2 and x100 is also true on this one example.
So then you just need to show all those possible examples and show that they're false.
Okay, that's closer to what I would like, but not exactly. Someone else, yes.
I think we do exactly like x2 is 1 in one example, x3 is 1 in one example, x4 is 1, x5 is 1, and then x100 is 1. So we have 5 examples.
Mhm.
So we'll need 5 examples and maybe one more to show that any other example won't work. Or maybe
Very close, very, very close. Just one more answer, yes.
But 5 more examples, turning each one to 0,
Mhm.
and then we will conclude that each of those ones are important to be 1, and all of the x2, x3, x4, x5, and x100 are included in the final formula. Yeah, I exactly mean this.
I'm just writing it out because I want to make sure that we are on the same page. So you said 5 examples. And the thing that I have done in each case is, in the first one, I have turned off x2. The second one, I have turned off x3, x4, x5, and x100. What does the first one tell you?
It tells just x2 is important, x2 is included.
x2 is relevant.
Relevant.
Yes. And what does the topmost one show you? This thing here.
These ones are relevant.
Some of these are relevant.
It basically says the things that are all 0 are irrelevant. Right? And the label for this one is a 1, and the label for all of them is a 0. And this is the right answer.
we need one more example where all of them are 0.
Why?
Because in this one we just know that all of this where it's 0 are irrelevant.
Because remember that this is all monotone conjunction. So I think your argument will not apply. So it turns out, first, the teacher gives a superset of the good variables. And it gives a set of, basically by constructing this one example where x2, x3, x4, x5, and x100 are all 1 and everything else is 0. And showing that the label is a 1. That says, ignore all the other features because they are not relevant here. And then it gives a list of 5 examples where in the first one, x2 is 0. It's exactly the same, but x2 is 0. And by showing that I don't know what's going on with the colors here, but by showing that the label is a 0, any reasonable learner will conclude that I need x2, x3, x4, x5, and x100. I need some subset of that. But if I remove x2, the label becomes 0. That means x2 is necessary. This example shows if I remove x3, the label becomes 0. So x3 is necessary. If I remove x4, the label 0. x4 is necessary. Same for x5 and same for x100. Another way to think about this is the first example is giving you the teacher is saying that these variables are sufficient, and the second set, the teacher is saying all these variables are necessary, and between necessary and sufficient, you're done. So any straightforward learning algorithm, you don't need a super intelligent learning algorithm. Any straightforward learning algorithm will produce the hidden conjunction exactly with these 6 examples. Teaching is far more efficient than active learning, right? Which is kind of cool. I mean, we should not really be doing machine learning. We should be doing machine being taught or something. Except modeling teaching is extremely difficult. There's very little literature in the AI machine learning community that actually tries to model teaching, because other than these sorts of small sort of toy examples, we can't do too much more. So this is the last you're going to hear about teaching of Boolean functions. Instead, we are going to be looking at protocol number 3. In this case, nature constructs examples. It picks instances randomly and gives them to the teacher. The teacher assigns labels to them. And I'm using the notation of this angle bracket here of example and a label. Okay, I hope this notation makes sense. So nature provides a bunch of examples. Some of them are positive, some of them are negative, and gives them to the learner and says, I don't know if these are necessary. I don't know if these are sufficient. These are all I have. Go figure. Basically, that's what we do with supervised learning, right? You get a collection of examples. There's no theorem that says, with this set of examples, you will discover a predictor for Apple's stock price tomorrow. So what can the learner do? Is there a easy learning algorithm that you can invent here? How do you discover the true function using these examples? Let's say that the learner knows this is a monotone conjunction. A similar sort of an idea works, right? You look at in the interest of time, I'm just going to go through, I'll tell you what a reasonable learner could do. First of all, in this particular data set, for this particular problem where you have monotone conjunction, first toss out all the examples that are labeled 0. And now only look at the examples that are labeled 1. In every example that's labeled a 1, turns out x100 shows up. So it seems like x100 is a relevant feature. Let's look at x99. Hey, look, this is an example where the label's a 1, but x99 is a 0. That means x99 couldn't possibly be relevant because there's one counterexample. So every 0 eliminates a corresponding feature. And every feature that is 1 for all the positive examples remains. So you have x100, and then what was that? X4, X3, X2, no, X5, X4, X3, X2. And hey, look, X1 also seems to show up as a 1 for every positive example. That means your learner will conclude by eliminating all those features that have any 0 for a positive example, the learner might conclude that the function is x1 and x2 and x3 and x4 and x5 and x100. Because there is no evidence that it can use using this data to get rid of x1. There's no way it can say that x1 is not relevant. x1 seems to show up every single time the label is a plus or labels a 1. So whenever the output's a 1, x1's a 1. So how could you possibly get rid of x1? How could any learner get rid of x1? That means that with the data that's available, we've only learned an approximation of the true function. We haven't discovered the true function. There's no guarantee that we'll discover the true function in the supervised learning setting, because your data might have a certain bias. In this case, the data has the bias that it just so happens that all the examples that are positive have the feature x1. Is this a problem? Any questions about this? Maybe. That's a possibility. Here I have only about 10 examples. Maybe if you had 11 examples, the first feature would have gotten eliminated. Maybe if I have 1 million examples, the first feature would have gotten eliminated. But there's no guarantee. Maybe not. Maybe the process that samples your examples has some inbuilt bias in it that never eliminates that feature because of some other issues. So there are two directions to go forward to analyze this, answer this question of how good is your learning algorithm. We could analyze this sort of a probabilistic intuition. In your training data, with 1 million examples, you never saw an example of x1 being 0 with a positive example. Maybe we don't care about all possible Boolean assignments to these features. We only care about examples that occur in nature. And nature, being the thing that sampled the examples, always put x1 equals 1 when the label was positive. Maybe in the future also, this is going to happen. And even if it does not, it's probably such a rare event that it doesn't matter. You will get like a 99% accurate classifier on most realistic examples that you will encounter in the future. Or maybe you'll get 100%, or maybe you'll get a small error and you're willing to live with that error. You're willing to tolerate a certain error on future examples, provided nature doesn't change its mind and decide in the future every example will have x1 equals 0. As long as nature is consistent with itself during the time it samples the training data and in the future, maybe life is good. This intuition leads to a formalism for machine learning called probably approximately correct learning, or PAC framework. It's a framework for formally defining the notion of learning and formally characterizing the goodness of learning algorithms. Another way to think about it is rather than thinking about it based on this collection of examples, you can imagine a learner that updates its internal belief as new examples comes along. So far, after having seen 10 examples, it seems like x1 seems to be present. Maybe the next example will change the hypothesis and x1 gets eliminated. And so over time, the learner improves as it sees more and more examples. In this case, the goodness is defined as how many examples does the learner need to encounter in nature before it stops making mistakes for good, where nature is randomly picking examples. This is an online process. Every time the learner encounters an example, it updates its internal belief, and then you have a new hypothesis and you ask, is this a perfect hypothesis? So essentially, we are asking, how many examples does it need to encounter to get the perfect hypothesis? This is what we're going to spend our next lecture on. We'll first look at mistake-driven and mistake-bound learning algorithms. And then from a theoretical perspective. And then I'll show you a practical mistake-driven learning algorithm that applies to linear classifiers, it turns out. And it's actually one of the oldest learning algorithms that looks like modern machine learning. And then we'll go back to theory and then go back to PAC and then build more algorithms from that. All right, I'll stop here. I'll hang around for any questions.